Welcome to Digital Design. We are now moving on to Chapter 3. Now, so far we've covered just digital circuits that you have an input, you get an output. And nothing ever changes. Unless you change the input, then the output will change. There's no kind of like memory associated with anything that happened in the past. And so that, the combinational circuits, is one aspect of digital design. We're going to go now into what's called sequential logic design. In other words, now we're going to add some memory to what we're doing. And in fact, one of the most important aspects is this is now computing, all right? It's important to understand combinational because that feeds the sequential. So let's take a look at the motivation for this. So the whole concept is, as I said, in combinational, you get inputs, maybe A and B. Your output will be never changing. It'll always be the same. If you have a 1 input here and a 0 output here, you will always get the same output, or the input A and B will always result in the same output, ever, all the time. You know, whatever your digital design is inside of that. But with sequential, when you put in the 1 and 0, you don't really know what the result might be because you have to know what the history is. In other words, you must know the sequence of past inputs to know what the output is. And so now we're going to introduce a concept of a state. And this is not like the United States of America. This is the state of the circuit. In other words, what is it like now? What was it a little while ago? And we're going to use a new building block called a flip-flop to store 1 bit. And of course, everybody knows a flip-flop is something on your foot, right? So we're going to combine these flip-flops into what we call a register. In other words, we're going to put several of these together and create a register. We're going to define all of how these states are changing by what we call a finite state machine. And then we're going to use that finite state machine to control our combinational logic. So let's get at it. So, well, this is a rather easy one, right? You've been on a plane before, right? I mean, I ask this because I have a graduate student working for me who the first time he ever went on a plane was at the age of 24. And we went to Los Angeles. Woo! It was pretty fun. But think about an airplane and the flight attendant call button. You press the button and the light goes on. And this is modern ones. Used to be in the old day, it was kind of like a toggle switch. Push it once, it turns on. Push it again, it turns off. But no, it's a new one now. You push the button and the blue light goes on. It doesn't matter how many times you push the call button, the blue light will go on. And to turn it off, you press the cancel button. Now you notice, this is not changing the input. This is actually an input that says when you press the button, it will go from 0 to 1 for a certain amount of time. And then based on that, this will stay on. And it will stay on until you get the push of this button, which will be going from 0 to 1 and then back to 0. And at that point, it'll work. So let's take a look at a timing of this. Oh, there we go. You push the button, and the bit storage goes in, and the blue light goes on. And it stays on when you release the button. And it will stay on until you press that button and basically transmit a 0 and turn it off. So if you look at the timing diagram, remember that, the timing diagram? Actually, let's draw the timing diagram. We'll do that really quick. That would be, what do we call the call button? We'll just say C-A-L-L. What the heck? So C-A-L-L, and when we press it and it goes from 1 0 to 1, and it'll stay like that for a while. And then I'll have a cancel. And later on I'll do that. And so our timing diagram for this, we'll call it BL, that you would expect it to go on and stay on until you actually press the button to turn it off. Now in this case I think it showed sending a 0 or storing a 0, but there may be a lot of stuff going on in there. I mean, you're basically going to have this button. By the way, if I said BL like that, it would look like that. What if I said instead BL and put a bar over it? What would that be? It would be the opposite, right? So in that case, I would expect it to work like this. I'm sorry, not BL. That was bad. Cancel. That's cancel, can you tell? And cancel is going on, and then I were to press it and it would generate a 0. So what is this? Oh, and I have the bar over it, right? What does that mean? We talked about this last class. Active low. And you could have things work either way. And if you were to look at the logic to make this work, well, it's not quite going to be a simple OR gate, right? It doesn't work like that because, remember, we press the button and then release it. You need some sort of feedback or storage device in the entire system. So we're going to have maybe some feedback. So does this do what we want? No, not really, because once you press S, right, and let's say anytime that we do this, that 1 will propagate to the output, right? And then that 1 will go back into the OR gate. And so basically it doesn't matter what this is at any other time. This will never change. There's no way to bring Q back to 0 at any time, since once this is 1 on the output, it'll always be 1 here. So maybe we need to do a little bit of modification, right? Well, here, this is an example of how we actually have this operate. Remember, there's always a slight gate delay from when it goes in. And then once you take it from S to 0, it doesn't matter what happens, it will always be 1 because this T will always be 1. So let's take a look at maybe if we put 2 together. Remember what the OR gate was, right? 0, 0 had an output of 1, and anything else had an output of 0. Does this circuit do what we want? Cross-coupled NOR gates. So let's take a look at this in a little bit more detail. All right, here we have 2 inputs. One we'll call S and one we'll call R. Now we really don't know what this T value is here or this Q value is. So we'll just leave that empty, or what we call floating right now. And let's say we change R to go from 0 to 1. What happens? Well, this forces Q to 0, because look at what we have here. We have S is 0, this input, let's go back up, this input was unknown. We have R now that we're changing to 1. So a NOR gate means that this output with a 1 will go immediately to 0. Do you agree? So then we will have a 1, the output goes to 0. Now we have a 0, 0 here. So our T goes to, from unknown or floating, it will go up to 1. So what we've done here now is we have an S and a reset. So set and reset. Now let us lower R. And what is our output? Well, Q is still going to be, oh, by the way, we have a 1 here, a 1 and a 0. So notice that a 1 and a 0, what does that give us as an output of? Still a 0, right? And so we still have a 0 and a 0 here. But look at the neat thing we do right here. Let's say that we have S, and we move S up to 1. So now we have 1, and this output is a 0, right? 1 and 0, it's going to be, so now that we're changing S to 1, right? 1 and 0, that's going to change this to a 0. A 0 will be fed here. A 0 and 0, remember, becomes a 1. Now we have a 1 and a 1 right here. And we definitely have our T is going to be 0 and our Q is going to be 1. So in other words, we have this set that actually creates an output on Q. And so very often you'll have the output of your sequential device is going to be the letter Q, and your input will be S. We'll also have another reset line going in. We're going to put this in a box, and we're going to call it a latch. And oh, by the way, if we were to ever change now S to 0, a 0 and a 1 is 0, so we'll get a 0 on the output here. We'll get the 0 over here. A 0 and a 0 is 1. And even though we change this S to a 0, our Q remains high. This remains the value logical 1, correct? This is, So what's the important thing to note here? And that is, the important thing to note is that we use this reset line to bring this to a known state. And here's the known state. All right? We hit the reset line here. The known state, here's our S is equal to 0. At this point, this is our value right now is 0. When we turn off the reset, we have our ready to go SR latch. And as soon as we give it a 1, we actually store that 1. No matter what S becomes, we still have stored it. Now, how do I unstore it? Well, let's take a look at this example again. Remember, we press the call button. Call button becomes 1, 0, and the R over here is input is a 0. So we're using this SR latch to light up this blue light. But, oh yeah, cancel equals 1. So that means, oh, by the way, we're holding it down too, right? So the problem is, if S1 and R1 are simultaneously changed, you don't know what the Q value will be, so we'll take a look at this. Let's say you set S1 and R1 to 1 at the exact same time. Then this will be 1, 0, and remember the NOR gate with a 1, 0 becomes a 0. So now this 0 comes in. 1, 0 becomes a 0, 0 comes in, and based on this, well, when will it ever go to 1, 1? So now if we remove S1 and R1 at the same time, now we have 0 here, 0 there, 0 here, 0 here, which means our outputs will be 1. both of these will become 1 at the same time. A 1 and a 0 is a 0. So they'll both become 0 at the same time. Or they'll transition from 0 to 1. And so sometimes you don't know what's going to happen. Is it this one or is it this one? And so the problem that you might have is that you might just have an oscillation of these two outputs. One path eventually will be slightly longer than the other one. Remember, there's a delay that is associated with this device here. And it might turn out that one is faster than the other, and then you'll either have this end up as a 0 or a 1. You don't know which one. So what we probably need to do is add some hardware to make sure that when we activate it, that we do it based on something. And what we often do is we worry more about, this is called a race condition. And so a way to fix this is to add another layer of logic that will allow us to, first of all, add a gate delay, but will also allow us to maybe later clock in the information at a known time. So a designer might try to avoid this by using an external circuit. In this case, you follow up with a OR gate. I'm sorry, with a NOT gate going through an AND. And again, we have a problem with gate delays. And so we can get, remember that glitch we talked about in the last class? You might have, because of these gate delays, you might have an additional little bit of information come in. And so what we do is we introduce with sequential circuits a device called, or an input called a clock. And so that means that we're going to rely on a clock signal to actually work with our input and say, we're going to let this input and this input settle, and then we will give you this clock signal which says, now latch this into our SR latch. So now we have an input S, an input R, and an output, and our output Q, and add on top of that a specific clock, which means now that we're synchronously making changes inside of this digital logic circuit. So what I would like you to do, let's see, is this good? I would like you to think about this, and assuming that each one of these gates is a 1 nanosecond delay, what I would like you to do is identify, and notice that we've got this labeled now S1, R1. By the way, this is, remember, that's T. We talked about that before. I want you to do a timing diagram, work with your neighbor. In fact, I'm going to make you guys do this up on the boards. So I want you to get in groups of 6 or so. No, that's just groups of 4. I'll make you do on different parts of the board. And right up on the board, what you think the timing diagram is going to look like for that, if at any time I do the S and do the R. I'll tell you what, I'll make it easy. Just do the S. Assume that R is 0 and everything is 0 to start with. So start with, where is it? There it is. Start with this to be a 0. Start with this to be a 1. So I'll help you out. S is 0. And later we're going to go up to 1. Assume that R is 1. And then we'll go down to 0. And then I'll give you the clock. do a quick clock, and then we'll do a clock. You know what? I'm going to do another one. Yeah, just do that. All right? So show me what S1, R1, Q, and T are going to be for this. All right? And do it up on the board, on the chalk, in groups of 4 or so. Thank you. All right, we're back. So, one thing I should ask, what did you learn about, or what did you see, experience, having you beat your head against this with me giving you only a little bit of information? You have to try and figure some stuff out on your own? So, here's the point. Did you maybe think about this more than just sitting here and absorbing it like some sort of sponge? All right, that's the whole reason why we break and do stuff like this in class. And in fact, that's I'm trying to make this a little bit more flipped-like. If I wanted you to do this in a truly flipped class, I would have made you watch a video first, and then come to class, and then we would do this. All right, so here is my solution, and a couple of things to point out. You really don't know what T and Q are until we actually give it the clock and allow things to settle down. This is a long line. Don't think that this is like a little halfway step, right? So our steady state for this will be, well, at this point, this is 0, this is 1, that's 1, this is 0, that's 1 at that point, that's 1, this is 0. This allows, eventually, really when you have a reset, the whole idea is that you want to set this to a 0, yes?
Why doesn't R1 have a 1 nanosecond delay after clock?
It does. So I didn't put it on, where did I put it? I put it on one of these up here. So at this point, there is a 1 nanosecond delay, then there is a 1 nanosecond delay, and then there's a 1 nanosecond delay. So yeah, it's the same thing. And I kind of squish it together. Now I noticed that some of you did a nice timing diagram out there, and that's fine, as long as you understand that like the clock pulse is a lot longer than 1 nanosecond. All right, 1 nanosecond for digital logic. In fact, what is a typical PC run at? What's its clock speed?
2.2 gigahertz.
2.2 gigahertz. How much time is that? I gotta do my calculator, and I gotta turn it sideways. All right, 2200000. That's mega 000 1 over e to the 10th. Crap, what does that mean? That's actually so it's sub nanosecond. So I guess that's all right. I'm used to working with like 6 megahertz clocks and 20 megahertz clocks and a lot longer clocks than that. All right. So here's the point. After we have this steady state, I wanted you to realize that even though you have S and you raised it, and you notice in my example I gave you, there was some time between S and the clock, right? Because typically, everything in digital circuits is based on that clock. You want the input signals, the combinational logic-ish type signals, to be steady. In other words, to not be wandering around. And then you give it the clock to record that. And that's the whole concept of sequential circuits. So at the clock itself, then that AND gate, 1 nanosecond later through the gate, goes from a 0 to a 1. And then 1 nanosecond later, it's adjusting T. And then 1 nanosecond later, it's changing the output for the lower NOR gate for Q. And that's the whole objective of this hands-on exercise we just did. Right? Let's go back to the notes. And these will be available for you to download and take a look at. Oops. And this just shows you that there's no glitch. Oh, I should show you this. So what we will see for a typical device like this is that we'll have S and R as our inputs. C, that's the clock. Our output will be Q and Q naught. In other words, sometimes it's important to know what the opposite of Q is going to be. Notice it's not T. It's not Q. It is not the value of T, but it's Q naught. Now, what we'll do is we'll also add onto this a little bit different. All right. So instead of having, notice how we started my problem with R as high, right, as reset. There's a way you could do that naturally, and that's just to put a NOT gate in there. And you only have one input instead of an S and an R. You have just one, and we'll call that D. D for data. And based on that, you remember this exercise I just showed you? That's basically what it is. And that will ensure, when you create a D-latch, it will ensure that you will never have some sort of funky situation where S and R are not what they should be. And here's a neat thing, is that this now forms the basis of all of your digital logic, sequential digital logic design, is what we call a D-latch. And this works out really well. If you look at the timing diagram for this, when you raise D, nothing changes until the clock comes in, and then the S input will go high. Notice that when the clock goes down, the S2 input goes back down, but by that time you have already passed the information along the T up here and then eventually to Q. One thing to note is that once you lower D, and you have D lower, and you introduce the clock again, then that causes R1 to basically clock as well, and it changes your Q down from 1 to 0. And this is the symbol for our D-latch, or what we call a D flip-flop. Easy enough? This is all the guts that you need associated with making a modern-day computer. Because now we could store what? One single bit of data. You put a whole bunch of these side by side, and you could store multiple bits of data. And you move the data around based on the what? The clock. So here's an example. Well, what if we want to... let's see, do I want to even go into this? I'm going to look at level-sensitive D-latches in a minute, so I'm going to go over this. So in a D flip-flop, we store values that only on the rising edge. So what we actually have inside, I should say, I showed you a D-latch. A flip-flop will then be created by taking the D-latch and the clock, and based on a NOT gate on this clock, you have a master and servant latch inside. And that way you can always ensure that whatever you latch on the D, for the D input for the first latch, it will be latched into this and then latched into the second one and stored based on not worrying about some of these problems earlier with level sensitive D latches. I don't want to go into this right now because it's a little bit too complex. I just want to get into the general concept of only latching things in on the rising edge of your clock. So if we take a look at this, here is our D input, and that's on the master. You notice that based on the clock being low, that means the input CM is going to be high. This will create for our output when you give this latch for the D for the master right here. At a certain delay, you'll get Q out. That serves as the source for this latch here. And based on the rising edge of that clock, that's when you will then clock this information, specifically the data that came out of QM. That's when you'll actually be latching that through to the QS. So if you have a situation like this, where you have D flip-flops one right after the other, and you want to serially provide data in and have it go from this flip-flop to that one, to that one, to that one, based on the rising edge of the clock, this data will then be clocked there, and it will be latched in on the next rising edge. And then it will be latched into here on the next rising edge. So if you look at this, on the rising edge of clock, all of these four flip-flops that are strung one right after the other are loaded simultaneously. And that's one of the advantages of using what we have, or what we have designed by having two individual D latches inside of our D flip-flop. So this is the typical drawing, or the typical design schematic that we have for the symbol for the D flip-flop that is rising edge triggered. And remember, when we put a bubble here, that's the same as a bar over that input. That would be a falling edge triggered D flip-flop. And what you'll notice here is that this is clock. When you have this little triangle thing here as an input, that will indicate that that is the clock input for a device. Now, one thing to notice, or that I should note, is that this is going to be the basic building block of all of our circuits now. Now, there are other things that you could talk about. JK flip-flop, as I've already talked about, RS latches. But this is the basic building block that we use for our digital logic. And I kind of pointed out the difference between a latch and a flip-flop. I don't want to go and belabor this point. Let's go on. Come on, come on, come on.